on. It's 7:5. Let's start. Let me know if you can see my screen, if you can hear me, if the font is okay. Okay, thank you. So today we'll be covering the chi-square test. We'll do it in two parts. In the first part, we'll just see whether two distributions, or we can say whether two samples are dependent. That would be one. The other case will be the goodness of it. That is, we'll check whether the particular distribution is the normal distribution or not. Similarly, you saw in the lectures that you can do it for other distributions as well. So we'll say goodness of it against a normal distribution. Okay, so the first part we can maybe use, let's say, chi-square test for independence. So for this one, we can use the iris dataset. I believe we have it in our repo. Iris. So we can load the dataset. We need the import numpy, pandas, and from maybe just SciPy will import chi-square as we go on. So we have this, we get our data set as read CSV path, and we can look at our data set. So we essentially have sepal length, sepal width, petal length, petal width, and we have these different species of iris that we have to predict. We, for our toy data set, we would like to test whether, let's say, the sepal length and the sepal width are independent or dependent on each other. So you would notice that we wanted to do chi-square because we have, let's say, nominal data or categorical data. We don't need it, let's say, if we have this continuous data set. So let's convert this data set into a nominal data set. For a nominal or an ordinal data set, we essentially mean that we should have discrete values, like yes, no values or some categories. So we can say, check, let's compare the length or width against their median values. Then we can see if the length, suppose, is greater than the median, we'll assign it a 1, otherwise we'll assign it to 0. So we can create two new columns in our data set. We can say df is equal to, we can first, let's say, just isolate just this much. We can say my df is just these two columns, sepal length and sepal width. And then we can say that my length underscore median is just df dot sepal length dot median. Similarly, the width median would be this much. We could print the two. So we have 5.8 and 3.0. Now we would like to essentially convert all of these values by comparing them to this. So the first one would become 0 because it is less than 5.8. The next one will be the same. And if there are values greater than that, it will be set to 1. So we can say df sepal length. We can also create a mask, but okay, is equal to df dot sepal length greater than length of median as type integer. So this thing by default, if we just run this much, if we run this much, it returns a Boolean series. Like if the first one is false, the second one is true. Since we want it to be an integer, we can just call as type integer. What happens is when you convert a Boolean into an integer, a false is taken as 0 and a true value is taken as 1. So we get a, rather than writing code for that, we just have a shortcut. So suppose we were to do it here, we have as type integer, so we get 0, 0, 0, 1, 1, 1, 0. This is what we want, right? So we do this for the sepal length, we do the same thing for width. And we have, so sepal length, width, length, width, length, width, and we can once again try df dot height. Okay, so we have our values. Let's cross check if everything is okay. Df dot sepal length dot value underscore counts. Yeah, so they're pretty much equal. So we have our two values. Now the next step in our chi-square test is to create the contingency table, right? Or the cross table that we call it. We want to know how many values have short length as well as short width. So a short value. The second one would be a short length and a longer width, a long length and a short width, and both long petal length and long petal width. So we will have four of these values. So how do we do that? We can essentially use pandas pivot function. We can call pd dot pivot table, and we can say, hey, my data is essentially this df value. I would like you to use the index as length. That is, so essentially pivot value will take the unique values in the sepal length and it will say, okay, against this 0, what are the different values of width that I get? Similarly, against the 1 value, what are the different values of width that I get? So it essentially counts it for us. So we will set, okay, use the sepal length as your index. And for columns, I would like you to use the sepal width. And the aggregation function is essentially length. That is, whatever number you find, just give it to me. Just count them. We supply the length function, and if we just run this much, you would notice we have sepal length 0, 1, sepal width 0, 1. So you have 38 values which are short, 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 long, long, short, long, long. So we have these four values. So since we only need the lower one, we can just work with that. We could in effect drop these and just say, give me the values. We could call this, let's say, the cross tab, and we say print cross tab. Okay, so this is now in NumPy array because we didn't anyway need the table, etc. Or we could keep it, it's the same thing. Now for the chi-square test, we can just use from scipy dot stats import what do we use, chi2 underscore contingency. So stats chi2 contingency. This function computes the chi-statistic and the p-value for the hypothesis test of independence of the observed frequency and in the contingency table. So what does it need? It essentially needs the contingency table that we have and corrections we don't have in our case. So let's see what we get. So if we have this chi2 contingency table, we can call chi2 contingency and we pass um, our cross table, and we say correction equal to false, and we see what we get. It returns the chi-square statistic, the p-value, and the degrees of freedom that it finds. So the degrees of freedom, if you would remember, it's just rows -1 into columns -1, which would be just 1 in this case. So if we catch the outputs, we get the chi-square value, we get the p-value, we get the degrees of freedom, and there was, I think, one more thing, the expected frequency. The expected frequency. In fact, the expected crosstab, maybe. So once we get this, let's see what we have for expected crosstab. So the expected crosstab says if these, suppose where, I mean, the other way around, then what would your frequencies look like? This is what it compares it against. Okay. This for our reference. Now we can set, suppose, our alpha to be 0.05 as we do normally, and we can just say if the p-value is greater than alpha, then print we reject the null hypothesis, that is, columns are independent, null hypothesis of columns being independent. And the other case would be we fail to reject the null hypothesis. Let's see what we get. We fail to reject this. So if we print our p-value, how much is it? Oh, it should be the other way around. Yeah, so our p-value is less than 0.05, so we can reject the null hypothesis of the columns being independent. There is some dependence between a flower's length and a flower's width. So I hope this much is clear. Now we can move on to the next one. The other side is, rather than having to sample that we want to compare for independence or dependence, suppose we just have a single distribution of numbers and we want to check whether it belongs to a particular distribution. In our case, suppose the normal distribution. So let's say we have, we take another data set. Where is it? Is it this one? So these are different temperature values that we have sampled. Okay, so 30 degrees, 20 degrees, 60 degrees, etc. This is the distribution of values. We would like to check whether the distribution of temperatures follows a normal distribution. So how can we use a chi-square test to do that? So let's import the data set once again. We can say this is chi-square goodness of fit against normal distribution. So our path is this. Our data set would be pd.pcsv path, and we can have a look at our data set, which is essentially just a series. We can just say, just drop the data set itself. Okay, so what is our null hypothesis? We didn't define it previously. It's best we do it this time. So our null hypothesis says that population is normal, and our alternate hypothesis says population isn't normal. By normal, we mean follows the normal distribution. We have our alpha to be 0.05, and in our this case, maybe we will need it or not, the degrees of freedom. Your degrees of freedom is essentially the number of bins minus essentially 1 minus p, and p in this case is 2 because you're using a I mean, we're comparing against a normal distribution, and normal distribution has two parameters. It has the mean and the standard deviation. So this will come later because we don't know the number of bins yet. Okay, so let's leave it at that. So um suppose we want to do this. So remember, the idea is that when you want to compare against a distribution, you break your sample, you bin your sample essentially, you break it into bins. So if we have this data set, suppose its length is, we have 365 temperatures, so essentially we have data for the entire year. We would like to bin it into different categories. So when you bin temperatures, we can break it into, let's say, okay, the temperature may be between -10 and 0 degrees. The next bin will be like 0 degrees to 10 degrees, and so on and so on. But we don't break the bins into equal temperatures. We want to bin it based on the normal distribution. So we want to create bins such based on the normal distribution, so that a data point has equal probability of falling into any bin. Okay, so if you look at the normal distribution, so we don't want to break it, for example, like this. That is one is standard deviation, two standard deviation like this. Okay, we want to bin it so that, because there is a very good probability of falling here, the bin near the center would be very thin because you have a good chance of falling here. The bin near the ends would be rather big because we want equal probability of falling that. So if we split it that way, we essentially want that, okay, in the first bin, which may be thin, let's say 10 temperatures are expected to fall here. Similarly, in this large bin, up to this point, another 10 days are expected to fall here, and so on and so forth. So depending on the distribution that you're comparing against, you want to bin that distribution similarly. So how can we create these bins? Since we know we want equal probability, we can use the PPF function for that. That is, which value gives me this particular probability. Okay, so suppose we want to create these bins, we can maintain a list for that. We can say um, for I in range 1 comma, how many intervals do we want? So by default, you would need at least five. You can, the base value is to use 5 because we want at least 5 temperatures for each bin. But because we have the entire year, we have the capability to do more. So let's do 12 because we have 12 months. So we can say interval is equal to 12, we will use 12 months. So we're saying in the range 1 to the number of intervals plus 1. So rather than starting at 0, we start at 1. We say um, bins, or maybe we can say value first. Value is equal to starts dot, let's maybe import this as well, from scipy dot starts import normal distribution. We want the normal distribution's PPF value, which is the inverse of your CDF. That is, if I give you a particular probability, return the X value that gives me that probability. So in this normal distribution, I have this PPF. I would like the area I times the area under first bin. So we haven't calculated this part yet. We're essentially saying, because I have equal area under each bin, if the first bin has, let's say, so if we go back maybe to the diagram, so we are saying for example, if I have, let's say, this amount of area under my first bin, the second one should have double that because they have equal area and I am in the second bin, so it is twice that. The third bin should have thrice the area, similarly, four times the area, and so on. So we only need the area under the first bin and then we can just duplicate that. So, whatever area we have under the first bin, we can have that. And we, for this particular normal distribution, we supply the mean and the standard deviation STD. So let's compute all of these values. Okay, so our mean in this case would be df dot this temperature dot mean, the mean of our temperature, and similarly the standard deviation would be df dot temperature dot standard deviation. So we have our mean, we have a standard deviation. Now the area under the first bin, how do we compute that? This is simply area under first bin is just 1 over the number of intervals. Okay, because remember that your full area essentially is 1. The probability curve for a normal distribution, the total area under the curve is 1. I'm saying I want equal area under each of the columns because we have 12 bins. I want 1 by 12 of the area in all of the bins. Okay, so or we can call it num intervals. That will be better. So we have number of intervals. You can maybe add a comment. Note total area under curve is 1. All right. So we have this particular value and we can just append this to our bin. So we can say bins dot append value. And then we can print our bins. What did we do wrong? We have attempted STD, parse out, did this. Oh, okay, so these are a particular bins. So it says that your first bin occurs at 6.88. So starting at 0, 0 to 6.88 is my first bin, 6.88 to 10 is my second bin, and so notice that the last bin is like 33 to infinity. In fact, in this case, it would be minus infinity to 6 rather than 0 to 6. Yes. So it says from 33 to infinity is your final bin, and it has the same thing. So because the normal distribution, it tapers off like this, it goes all the way to infinity. So these are our bins. Now, we would like to categorize every temperature in a particular bin. So let's suppose we have this first temperature, 31 degrees centigrade. Which bin should it be in? So it can be in this. So we just keep moving on through this till we hit a point greater than it. So 33 is greater than it. So it would belong in this particular bin, 29 to 33. This would be its bin. Okay. So let's convert this particular data frame into the bin data set because we have our bins. We can define a function. We can say define bin element. You could also do it the other way. You first define the bins, and pandas also gives you a function that is given these particular bins, give me the bin data. But let's do it this way. We have a particular x value and we can supply the bins and we say return me the particular bin. So we can say for I comma bin in enumerate bins. So these values, the bins, we can say if x is less or equal to bin, you return, should we return, this would be incorrect. For I comma bin, enumerate bin, what do we want? So suppose we supply 6.88 and we pass, no, suppose we supply 30 and we go through this loop. The first one is wrong, the second is wrong, the third is wrong, and so on, so on, so on, because these are in increasing value. We can say assumes bins are sorted. So because these are in increasing order, the first time X is less than a bin. So 24, no, 26, no, 29, no. At 33, your X value would be less than your bin, so you can return I. So let's maybe test it out. We can say element, we pass 30, we pass bins. What do we get? We get 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we get the correct answer. Okay, the 10th bin. So we can now apply this function to our data set, this one. So we can say df dot bins is equal to df dot temperature, or maybe for consistency, df temperature dot apply. We want to apply what? We want to apply this particular function. So how do you do that? In Lambda, you pass a Lambda function. Lambda function says, okay, if you give me an X value, what do you want me to do with the X value? I want you to apply bin element on the X value, and the bins are predefined in this case. Okay, so this should give us our values. We can say df dot head, and we get our values. So every temperature is now bin. This is in bin 10, bin 6, bin 1, and so on. Now, we would like to essentially create the cross table as we did before. In this time, our cross table is essentially a single row. We want to say how many um, data instances fall under each bin, compare that against the expected number of data instances in each bin. So the expected by design should be like 1 by the total number of the total data frame size, right? Because we divided it specifically so that every interval has the equal probability. Okay. So if we were to do this, so how do we create this particular cross table? We can just say we have these bins. I would like you to group by the bins. So we can say df dot group by, please group by the bins, and I would just like the count. So if you just print this, it gives us this clean value, that is bin 0 has 27 values, bin 1 has 35 values, so on and so forth. So for the 12 months, not the months, we just use 12 intervals. We, for our 12 intervals, we have these number of days in each interval. Okay, so we can just save this. We can say just give me um, these particular values and just flatten it out. Mm, like this. So 23, 27, 35. Let's in fact try without this. Maybe the function accepts it. Let's keep it like this. Okay, so this is our bins, these are values. So we can call them our cross tab is equal to this much. Now we want the expected cross tab. The expected cross tab, as we said, it has the same shape as this thing. The only thing is every value has the same number of data points as by design. So we can essentially say that is why I wanted to create a numpy function, because it's easier to work with. We can just say values dot flatten. So if we have this sort of data, we can just say, give me a column of ones, np dot ones. Give me a column of ones. When you say like, I'm saying use the same shape as this cross table. Use the same shape as this cross table. So this is, if suppose we were to do it here, you get something like this. Wait, not like this. Yeah, so you have a column of ones like this. Now we just want to divide it by the length of our data frame. We have this, we multiply it by the length of our data frame, and we divide by the number of intervals. Num intervals. So this is essentially equal probability in every bin. So we have both of these values. If we print, suppose this, and we print the expected crosstab, we see this. So 22, 33, 47, so on. We have 44, 35, similarly, and so on. We could, again, do an integer thing here to make this the same. If we do ones like this, length of df, number of intervals, shouldn't this give you an integer? 30. Wait. There's an error here. Oh, spelling. Yeah. So by default, we should have an equal number of entries in each bin, so 30, and this is the expected one. So this number will change depending on your probability distribution that you're comparing against. Not a uniform distribution would have a different number in each bin. Normal distribution has a different number in each bin. Once we have this, we can just use the function, the chi-square test, to check what happens. So we can say from scipy dot starts import chi-square. So this is a different function than our earlier case, because in this case we know the expected crosstab. Earlier we did not know that, so you use a different function there which calculates it for you. Okay, so we say chi-square. It performs the Pearson's chi-square test. What does it take? It takes the f observed, the f expected, the degrees of freedom, and what does it return? It returns the chi-square value. It returns the chi-square statistic and the p-value. So we can say chi comma p-value is returned by this thing. We have to supply it f observed. F observed is our normal crosstab. Our f expected is our expected crosstab, and our degree of freedom in this case is, we can maybe define it up here. Our degree of freedom is number of intervals minus 1 minus p, and p in our case is 2, mean, and std. Because of that, we have p equal to 2, so this minus this minus this, so we supply degree of freedom here, we get our values. We had our alpha defined earlier, so we can say if we just print the p-value first, then we'll see. Got an unexpected DOF. Did you not need the DOF? DDOF, okay. Mm, 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 mm. For each, there is a sum of the observed must agree with the sum of this to relevance tolerance of this, but the percent differences are this much. Everything looks fine. And the degrees of freedom are also. Oh, I think we should just pass 2 in this case. It can maybe do this for us. Sum of observed frequencies must agree with the sum of the tolerance of this, but percent differences are this, so that's weird. SciPy stats chi-square. Delta degrees of freedom. Adjustment to degrees of freedom for p-value. The p-value is computed using chi-square of k minus 1 minus. Okay, so we just passed 2 in this case. So that part was correct. So you don't need this. If an integer, the axis of the input which to compute this, the if none is raveled, okay, sum check. Whether to perform a sum check, that is, this is if true, there is an error, the sum check, maybe we can pass it false in this case. Hmm. So we get a p-value of 0.85, much more than our alpha value. So we can just say if p-value is less than alpha, we can say print reject the null hypothesis, which was our initial edge 0. Otherwise, say print fail to reject the null hypothesis. Just give me a minute. Okay, so to summarize, we conducted two toy experiments for the chi-square test. The first one was, can you compare whether two of your columns are dependent or independent? You first start out with your null hypothesis, that is, they are independent, and the other cases that they are not independent. I mean, you fail to reject that. You take your continuous values and you convert them into discrete values by comparing against the median. You create your crosstab, which essentially says how many you bin it, saying that the length is short, the width is short, the length is short, the width is long, and you get these four values. You supply your contingency table to chi-square contingency, and that essentially checks whether the two columns that you're comparing, whether they are dependent or independent. In this case, yeah, it was less than alpha, so we can safely reject the null hypothesis. The second case was, can you test whether a particular distribution is a good fit for a normal distribution? To do that, we took the temperature values from a entire year. We have 365 values. So our null hypothesis was that the population is normal, and the alternate saying is that it is not normal. So how do you perform the chi-square test? You essentially bin the probability distribution that you want to compare against. We had the normal distribution. We decided to bin it into 12 bins. Every bin by design should have an equal probability of a point landing into that bin. So it's very easy to do that. The total probability under the curve is 1. So every curve should have 1 by this much probability under it. So the way we decide the x values that would give us those particular bins is we take the norm.ppf. ppf is the inverse of your CDF value. Your CDF value takes the x value and returns the probability. PPF is the opposite. It takes probability and gives you the x value. So you say, okay, my area under the curve is this much. My first bin should have 1 into area under curve. My second bin should have twice the area under curve. Third bin should have thrice the area under the curve, and so on. So you get your individual values and you supply and you store them in the bin. By nature, these are increasing values because we are going for increasing probability. Okay. So we start from negative infinity to 6, then to 10, 13, so on, and we get these 12 bins. We convert all of our continuous values into our bin values by comparing against the bins. So 31 goes to bin number 10, 21 goes to bin number 6, and so on. So once we have these bins, we want to say, okay, how many values fall under bin number 10? How many temperature values fall under bin number 1? It's quite easy to do that. We just use a group by function over the bins. This would return a series by default, but because we just wanted the numpy values, so we just say, okay, give me the values and flatten the array. So it gives us something like this. To compare it against an expected value, we just need an array of the same shape. So we use ones like. Ones like essentially means the like function copies the shape, and one says, okay, I want a 1 in every value. To that 1, we multiply this norm expected frequency. The expected frequency by design, because everyone has an equal probability, we say what is the length of your data frame, that is the length of your sample, divided by the number of intervals, which is 30 in our case. We use an integer division to keep everything in a for integer arithmetic. So these were our
normal values, the cross type value, this is our expected values, and then you can just use a chi-square test to check whether your p-value is less than alpha. In this case, it was not the case. The p-value was much larger compared to alpha, so we failed to reject that the population is normal. I hope everything is clear. We can stop recording. Okay, if there are no confusions, so I'll end the meeting. See you all next week.